Welcome to the Global Composites Express webinar series. My name is Wenbin Yu. I'm the director of the Composite Design and Manufacturing Hub. I'm delighted to have you all join us today. This webinar series examines the history, the present capability, and the future of composite science and technology. Our goal is to share the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. Our center is located in the Indiana Manufacturing Institute. We welcome all of you to visit us and explore the cutting-edge facilities and resources available at our center. At CDM Hub, our mission is to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. Our vision is for CDM Hub to become the premier resource for composite design and manufacturing. To achieve this mission, we have developed a powerful website called cdmhub.org, which serves as a platform for the composite community to collaborate and innovate together. We invite you to join cdmhub.org and take advantage of all the resources and knowledge available on our website. This webinar series is made possible by the generous support of our sponsors, including Dassault Systems, Cytec Solvay, and Anna Swift. We extend our heartfelt gratitude to our sponsors and acknowledge their commitment to advancing the field of composites. We also welcome other organizations to join them and join us in supporting the global composite community. Together, we can create a brighter future for our field. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will be about 45 minutes, followed by a 10-minute question and answer section. All attendees are muted. We ask you to submit your questions through the Q&A box. To ensure our speaker has adequate time to address questions, your questions may be summarized or rephrased, but rest assured that all questions will be forwarded to the speaker for their answers at their discretion. Now, I would like to invite Professor and Dr. Pabst to introduce our distinguished speaker for today's webinar.
Thank you, Wenbin. I'm delighted to introduce to you Dr. Ajit Roy. He is the computational group leader at the Materials and Manufacturing Directorate of the United States Air Force Research Laboratory. His research area is materials innovations and development in structural, thermal, and electronic materials. His focus is in the integration of multiscale computational methods to materials processing for accelerated materials development and technology transition. He was a pioneer in the carbon foam technology and nanoporous carbon as multifunctional materials for coatings, flexible electronics, battery electrodes. His durable thermal interface concept transitioned to a commercial product. He has almost 30,000 Google citations of his published work and is recipient of the American Society of Composites Outstanding Research Award, the Fellow of the Air Force Research Laboratory, AIAA, American Society of Mechanical Engineers, and American Society for Composites. He serves on journal editorial boards and advisory panels across the country. He received his PhD in engineering mechanics from the University of Minnesota in 1985. With that introduction, I'm delighted to turn the floor to Dr. Ajit Roy.
Thank you, Professor Pipes. It's an honor to get an introduction from you and totally humbled by your kind introduction. with this, it's my honor to be part of this distinguished webinar series. Let me share my screen. Today, I'm going to talk about bottom-up composite material design for multifunctionality. Composites, the idea of composites, material hybridization for improving materials performance. That's the idea. And it has been, it's not new. And over the last 3 or 4 decades, there's a lot of advancement happening. And in the past, the focus has been on the structural performance side. And with these advancements, with the pioneering contribution by many contributors, including Dr. Byron Price from Purdue, composites has come to mainstream as an emerging material. And that gives us the opportunity to go into other functionality and explore and insert this material concept for other application domain. So that's what I'm going to talk about, bringing not only structural, but other functionalities that we can offer with this material hybridization concept. And my focus will be on bottom-up composite material design. Why it is bottom-up, I'm going to talk about in a few minutes. So next, will be to speaking of the functionality, I want to give you an example. For example, this is electronics for high impact scenario. This video I'm showing is that electronics packaging undergoing high acceleration impact. This particular test was done 10,000 G. G means 1 G means if you are dropping a cell phone, that's 1 G. So imagine this is a much higher accelerated rate testing. And in the video, I saw some pieces flying out. That means the interconnects are failing traces. So you need to have new type of material that can sustain high strain rate at the same time provide the electrical connectivity and other properties. And local heating happens, you should be able to sustain that kind of heating locally to offer performance. So with this, I'm going to focus on this concept for obviously you need flexible electronics. The nanomaterials based flexible electronics concept by CNT mesh. That I'm going to talk and use this example quite often. Another example I want to bring up is that, say, electronics packaging for high temperature environment. For example, engine performance monitoring, that's a big issue because if you can monitor in real time the engine performance by putting sensors in hot zone area, that will give you a close handle in terms of maintenance and real-time repair issue, and hence reduce the downtime on the system performance. In this concept, this kind of sensor ideal or desirable goal is to perform 2,000 hours or 50,000 cycles, but currently there's no other materials that can offer this kind of durability. Current materials, electronics packaging offers only a few hundred cycles. So with this, with the nanomaterials and materials hybridization, there's some opportunity space. That's what I need to talk. Here is I want to bring up why bottom up. Bottom up means material design from small scale, means atomistic scale. So if you do hybridization, that's what the concept is all composite is all about. Then I want to illustrate this concept with this classic example of three-point bend test. If you look at the three-point bend test, all the say action materials are exerting or are going under high strain rate or doing all the work under the pointed load. So in other words, you need materials, high performance materials near the point load applied, whereas other away points away from this applied load, you don't need that kind of high performance materials. That's the idea of hybridization to optimize materials usage as well as performance. And if you bring this hybridization as small as possible, then you boost up the materials uses efficiency as also device performance. I'm going to illustrate that, as I said before, this is a network of carbon nanotube, and I'm going to make the point what is we are after and why this dispersion of carbon nanotube is not adequate. And similar thing with these multifunctional materials that we are uh, talking about here. So TPS these days is not just oxidation resistance or temperature tolerant material, but also you need to have other functionality like thermal and so forth. This with this nanomaterials concept, we offer those kind of functionality. That's what I'm going to illustrate in this talk. So let me start with the very classic example that carbon nanofiber reinforced polymer composites. You know, carbon fibers are quite strong structurally as well as it has decent thermal and electrical properties along the fiber direction. Whereas when these are embedded in polymer, their transverse properties are not as good as in the axial direction, both in structurally as well as thermal or electrical properties. People to work on this, people have been in the community trying to uh, grow carbon nanotube, decorate carbon fiber with carbon nanotube like depicted here, and with the hope that this, when they are embedded in polymer, this carbon nanotube will make contact and create a pathway, and also this contact will provide some structural rigidity to improve the structural as well as thermal and other electrical properties. But in reality, the achievement has not happened to the level to the expectation. Case in point is that, for example, epoxy strength is 6 KSI, whereas carbon nanotube is 40 GPa or 40 MPa versus 40 GPa. So 1,000 times stronger carbon nanotube is stronger. So if you mix, say 1%, you expect the proportionality strength will be go up, but that doesn't happen because of all the interface issues, how they are connected to each other. Same is the story for thermal conductivity. Thermal conductivity for epoxy is 0.3 watts per meter Kelvin, whereas CNT conservative estimate is 1,000 watt per meter Kelvin. So even when 1% of carbon nanotube dispersed in polymer, you would expect a lot of improvement. But that doesn't, it has not been realized because of this interface issue that I'm going to discuss. Another key driver in this interface design concept, and also why carbon nanotube network and with the connected network will offer the higher performance as compared to dispersed carbon nanotube. Let me illustrate this with this example here. Say, if you have, carbon nanotube are not infinitely long, they're discontinuous, and when they are dispersed in polymer, they are just dispersed in polymer, not necessarily they are making contact to each other. Whereas if you can ensure these carbon nanotubes are interconnected with welded junction, if you will, for example, then what will happen, say in case of this crack propagating, if they are not robustly connected in all the nanotube mesh, then this individual nanotube will try to deter crack propagation, but not necessarily all other nanotube will contribute unless their network is robustly interconnected with welded junction and so forth. That's the concept. So with this network concept, we can boost up the properties that we are missing in just mixing carbon nanotube. So in traditional processing route, like you disperse carbon nanotube in polymer and hope they will provide the improvement, but that doesn't happen because as soon as you put nanotube in polymer, polymer get ingest between carbon nanotube, hence interface will not be as robust. Whereas if you, before you put the nanotube network in polymer, you create the network junction by either heat treating to weld the junctions or decorate the nanotube with some other metal and other things, other materials. Then you, by heat treating, that creates a network or welded junction interconnecting nanotube. After you create the network, then you infuse polymer mesh, no, nanotube, nanotube network infused with polymer, and then you have the integrity of network nanotube, and you will get the higher performance. And that's the process we have demonstrated with the, and we have patented this process as well. So this is the what I am talking about. You create the network for junction of nanotube, then infuse polymer, then you get the improved properties. So this is the example of the such process. This is the bonded joint, and this idea I got motivated from by Dr. Ed Silverman from Northrop Grumman. He told me that if the bonded joint thermal through thickness thermal conductivity can be improved, say traditionally say 1 watt per meter Kelvin to 10 watts, there's a big savings, say $1 million. That's what he says per satellites. So that's the big savings over the lifetime of a satellite. So we developed a process. We used aligned carbon nanotube, then infused polymer and etched away polymer from the tips of the carbon nanotube to make a thermal contact. And that's what we came up with from our finite element calculations to create the thermal contact through the medium, through thickness of the bonded joint. And in this process, after etching polymer, then we decorated tips of carbon nanotube metallization, and it's called ion etching, and that is documented here. And then we cured the bonded joint. And with doing so, we created a thermally conductive bonded joint that is applicable to satellite application, satellite design and structural component. And we measure thermal conductivity through thickness over 260 watt per meter Kelvin as compared to without such engineering, nanometers engineering is near 1 or 2 watts per meter Kelvin. So if you do the right interface, that's the key towards improving properties with the nanomaterials. Then indeed you can achieve the property that is missing without doing proper engineering. So we want to go looking at this problem a little further. So from these measured properties, we back calculated low interface between carbon nanotube and this sheet, conducting sheet. And the interface resistance comes out to about 6 in this unit. Whereas if you do the right engineering, you can go to less than 1. So still there's a room for improvement even if we showed good success in this design. That brings up the point of looking this problem more atomistically, hence bottom-up design. So that's the nutshell, the message I'm conveying here. So what is the bottleneck and what is the challenge? So if we want to pursue this network carbon nanotube mesh, so how do you design the interface? As I showed in the previous example, the interface is the key. Unless you do the right interface design, you will not achieve the properties. So there's a good, nice work over a decade ago. This is the work of dispersed carbon nanotube. Nothing is done on interface design, just laying one on top of the other. And with AFM, atomic force microscopy, they measure the electrical resistance of carbon nanotube along the length, then at the junction. If you follow the nanotube across the junction, same nanotube, there's not much of change. Whereas if you jump from one nanotube to the other nanotube through the junction, there's a big resistance. This interface resistance is quite high unless you tailor this interface properly with nanoscale material design. Same is this is for electrical. Same is the case for thermal, and that interface resistance is very high as compared to the individual carbon nanotube resistance. So that's the motivation of designing properly the interface of these nanomaterials to improve the overall performance of in the basket. So we have been doing this, we have done extensive work in this area and with nanomaterials for improving other properties, not only structural, but other properties. And in that context, nanocarbon materials, I'm very passionate about it, and that gives you a lot of opportunities. We have done many work in different areas, sensor and other electronics. But for this work, I'm going to focus on 3 areas: structural, thermal, and electrical properties. So first, let me focus on the structure. Means I'm looking at the strength point of view. So from strength point of view, how do you create this kind of junction or nanotube? There's a way to look at the junction optimization. Euler law for CNT nanostructure based on sp2 bond means nanotubes are planarily junction to each other. For sp2 bonded nanotubes with open ends, with the energy, we can benchmark to 0 level called bond surplus 0. All carbon nanotubes in this case are 6 member ring. And then when you look at the other geometry, half-capped CNT means this end is capped, then you no longer have 6 member ring. There's some 5 member ring and so forth. So, and you need 6 of them. So that brings bond surplus minus 6. If you do double cap CNT or fluorine, because of same concept of 7 member ring accommodation, 5 member ring accommodation to 6 member ring, so bond surplus becomes 12. For junction like graphene to CNT, you need 7 member ring that brings bond surplus plus 6. For CNT-CNT junction, such abnormality means deviation from 6 member to 7 or 5, that bond surplus minimum surface energy of surface topology brings bond surplus to plus 12. That's the basic design concept in terms of creating junction from strength point of view for carbon nanotube structure. So we have done the strength prediction with this surface topology optimization, and that is done adapting the tools we have developed, molecular mechanics and molecular dynamics. Molecular mechanics in this case is this similar to molecular dynamics, but we took away the dynamics part just to focus on static problem. And combining these two, we not only can create the junction as well as analyze the strength. This is the case for graphene with carbon nanotube junction. Of course, carbon nanotube has different chirality, and that gives the challenge in terms of, as I said before, to create this kind of junctions, we need 7 member rings to accommodate this kind of curvature. And depending on chirality of nanotube, the distribution of this 7 member ring around the circumference of the junction gets sometimes irregular, not uniformly distributed, unless it is armchair, 6-6 ring, and where these are equally distributed around the junction circumference. So with this, we did the calculation for strength prediction for different chirality junction. As you see, for armchair, 6-6 ring, these 7-member defects are regularly uniformly distributed across the junction area, and that gives as like a structural mechanics. When your defects are uniformly distributed, that gives you a higher strength or load carrying capability. Same is the true here. As you see, these rings, when they are regularly defects are regularly distributed, we get higher strength as compared to the other irregular distribution. So that's the design area in terms of if you want to join graphene to CNT. But more practical option. Oh, so one more thing I want to say. Those calculations are very idealistic case, means very pristine CNT, but in reality that doesn't happen. In the when we compare our prediction with the measurement, this is the work we have done in collaboration with Professor Jun Lu from Rice University. He did with AFM the strength measurement. The strength prediction is quite low, 2 order of magnitude, I would say, lower than what we are predicting. Reason being there are many other attributes, irregularity, place when you the experiment because of some, for example, some nanotubes are not being attached to the carbon fiber surface, or some are with defects, and with all these factors play a role in terms of what we measure. So then we have a long way to go to relate our computation and small k to the real measurement properties. But computation gives you a trend that will be guiding principle for designing materials nonetheless. So next, we want to go to a more practical example. As I said, carbon nanotube mesh. That's the idea. So when you want to join the carbon nanotube next to each other, as I said, all the defects you need to optimize 7-member, 8-member, or 5-member, and their distribution of it. And their distribution depends on how they are connected to each other, either fully fused or barely fused. And so we look at all these problems, and with this calculation, we find, as you see, barely fused junction gives you higher strength as compared to fully fused. Although one may assume that, okay, fully fused will be more robust. That's not the case. Reason being, when you are fully fused, you are destroying the nanotube integrity, hence its load carrying capability as compared to barely fused, and where you retain as much of bond integrity within the carbon nanotube or atomistic configuration than the fully fused. And in from practical point of view, this makes sense because from processing point of view, it's also easier to fabricate because you just lay carbon nanotube on top of each other, then do heat treatment. That would create a welded junction versus creating this kind of junction is more tedious because that requires more process control and also computation from doping and so forth. So with this computation gives a guidance to processing engineers how to design this kind of junction. And this, we are the first time to show that overlap junction creation is much easier and also from a strength point of view, robust as compared to fully fused junction. Now I'm going to go to thermal part. So what I said, thermal mixing carbon nanotube to each other not doesn't give you the improvement on thermal conductivity. So we want to look this problem very carefully. As I said before, this is all also a thermal interface design issue. So this is the case. We are putting two nanotubes next to each other, and we are hitting one and taking heat out. And after equilibrating the situation, we see there's a disparity in temperature, even next the wall next to each other of this cold and hot nanotube. That means there's a significant thermal resistance at the interface of these two junctions. So other option will be to functionalize this nanotube walls instead of van der Waals walls. You can functionalize with different molecules, either small molecule, big molecule, rigid molecule, and soft molecule. We look at those problems. Of course, you increase the degree of functionalization that improve the interface thermal conductance, but still we are not seeing the diminished to zero. That means this molecule is not, there's a room for selecting this molecule. So we look at different type of molecules. We find that smaller molecules and rigid molecules gives you higher conductance than on van der Waals properties. But still, there's a room. How do you select these molecules? We then formulated, look at this problem more carefully with a weight packet calculation, or phonon weight packet. In this calculation process, we look at energy specific, which can send one specific frequency of phonon and look at the transmission coefficient. And that's transmission coefficient will give you the indication of how robust the interface conductance is. So at the where you put the molecule for functionalization, that's the side. There's some energy will transmit, some will reflect back, and that can be assessed properly, and their efficiency can be assessed properly by looking at their dispersion curve. Phonon dispersion curve, the slope of the phonon dispersion curve is the group velocity, and that group velocity is integrally proportional or follows the transmission coefficient in respect of all the different molecules we have here. So here is the design selection criteria of molecules, you can pick a molecule that gives you higher group velocity as compared to low velocity. And the group velocity is dependent on proportionally to how the bond modulus of the junction of the molecules and inversely proportional to the mass. So smaller the mass and higher the bond energy, that will give you a higher thermal conductance. So, so in case of carbon nanotube, you to maximize that, you need to have the difference between this mass and also bond. You need a similar molecule. If it is carbon, it has to be carbon. And that's the ideal interface. And we created those interfaces, but those are very tedious and time consuming and practically probably not feasible. Instead, we can adapt to metallization because metal is conductive. And what if you put metal at the interface? And that's where design comes in. That can be assessed through density of state spectra, phonon density of state, overlap of the density of state of the metal you are decorating with or putting interface with the nanotube spectra, phonon spectra gives you a higher improved interface conductance. That we have done. Oh, so you can pick different metal, gold, copper, aluminum, and so forth. We demonstrated that with gold. Gold melting point is over 1,000, whereas carbon disintegrate after 550 degrees Celsius. So how do you tackle this issue? But there's a brighter side. If you make it nano size, in this case is 5 or 4 nanometer, we see melting temperature of gold drops to 260 and so. So with this, we decorated nanotube with gold nanoparticles of different sizes, and also with other metal. And we found, as we predicted computationally, chromium, titanium, copper much better than the gold. And that is validated experimentally. We measured those properties. And those measurements are also done on micro scale testing device we have developed, and that is patented in this in our laboratory. Now, final topic, I'm going to electrical property that we looked at the interface by tight binding non-equilibrium Green's function, and we have published this work. You can follow. Because of time, I'm not going to talk about the methodology in this case. But what I'd like to say, in case of this junction design for electrical conductance at the interface, electron orbital plays a role. Overlap of electron orbital dictates the conductivity, electrical conductance. If you make carbon nanotube smaller, their electron orbital repels out of the circumference, hence the higher overlap. And that's what we observe. At the same time, if you put some molecule in between, that kills the conductance. So the design point of view, smaller nanotube and digging close to each other without any polymer functionalization will give you higher electrical conductance. Other option will be metallization. You can use different metal to decorate the nanotube interface and infuse them, and they, along the whole, they gives a higher improvement, 200 to 400 for infuse in case of titanium and copper, silver. One point I like to make that in thermal, we saw that titanium is preferred metal for interface welding, and so is the case of electrical. So that gives you the simultaneous functionality that I mentioned at the beginning of my talk. So after all this, we made some materials without functionalization. Then we tested them. This is the moment of truth. split Hopkinson bar pressure test, high impact, high GA testing. And we found that with this CNT mesh optimization on interface design and putting in polymer, creating a CNT ink, this material survived high impact scenario, whereas without modification, we didn't get any signal. So, and other topics, similar topics, there's some issues for metal, non-metal interface, where electron-phonon coupling plays a role, where Weizmann-Franz law, which is good for homogeneous materials, would not work because it's a heterogeneous material interface. And that's where electron-phonon coupling, this parameter needs to be predicted. And that's the open field still being done. Other topic point I like to make that as we make from small scale to a bigger scale, this size of this individual material constituent plays a role. So how do you say what is the design factor? So if in case of thermal, if the phonometric path, if the material is very pristine, then phonometric path will be very large. When it's a defective, phonometric path is small. So if phonometric path is small as compared to the size of this domain, then interface plays a role. Whereas this phonometric path is large, means pristine material, then interface will not be an issue. That's the design rules we can follow. So I'd like to summarize. This is what I want to say here or emphasize there. Atomistic scale material hybridization gives you opportunity, enormous opportunity for not only structural but other functionality. You can begin in the materials performance domain. And principle for this design concept will be the local dissipation mechanism. In case of electrical is electron orbital, for thermal is a phono energy spectra, and for mechanical is a low cost field mitigation. With that, I'd like to thank all my collaborators. I have the privilege of working with very distinguished and smart people, both internally at AFRL and on the external. Thank you very much.
Thank you, everybody. We'll look forward to seeing everybody again on April 18th.